Welcome to today's deep dive. Every time you board a commercial flight, the titanium alloy holding the engine mounts together it's basically fighting this invisible microscopic war against itself.
It really is.
Right, so today's deep dive is into this fascinating 2026 materials science paper on Ti-6Al-4V. And our mission today is to uncover how aerospace engineers literally weaponize that internal tension and how they measure these trapped forces to keep the structures you fly on from just, ripping apart.
Exactly. And they do this deliberately through a manufacturing process called one-sided dimpling. So the researchers take a 16-millimeter steel sphere, and they basically drive it a full millimeter deep into a solid titanium plate.
Wow.
Yeah, using 13 kilonewtons of force to do it.
I mean, that is just a massive localized impact.
It is. And what's fascinating here is why they do it. This indentation creates compressive residual stress right on the surface, which heroically stops fatigue cracks from forming in the first place.
Okay, let's unpack this for a second. Because mechanically, you're squishing the atomic lattice closer together at the impact site, like pressing down the dead center of a tightly packed sandwich.
Right. That's a really great way to picture it.
The fillings have to go somewhere, right? I mean, physics dictates that the energy doesn't just vanish. So to maintain equilibrium, the metal underneath that dimple actually gets forced outward, creating this deep, hidden zone of tensile stress.
Exactly. So the surface gets this awesome structural armor, but the bulk material underneath really takes on the burden.
Which sounds, pretty dangerous.
Well, it is an engineering challenge. You now have this hidden stretching that's constantly trying to pull the metal apart from the inside out.
So that brings up the obvious measurement problem. Like, how do you quantify a force you literally can't see?
Right. Well, the paper details two specific methods for reading the surface. The first one is ESPI.
And that's where they drill a tiny hole and use laser interferometry, yeah.
You got it. Drilling basically severs those stressed atomic bonds.
So the surrounding metal microscopically snaps back.
Exactly. It recoils, and the laser measures that macro displacement. But the second method, FIB-DIC, uses a focused ion beam.
Okay, wait.
Yeah.
They use an ion beam to carve these microscopic rings and track the strain relief. But doesn't blasting titanium with an ion beam generate, a ton of heat?
It does.
So wouldn't that atomic disruption alter the exact stress state they're actually trying to measure?
I mean, that's a very valid concern. It's exactly why the scale of the measurement is just so critical here.
Okay, so how do they fix it?
Well, FIB-DIC operates at such a microscopic level that you're picking up all this chaotic, granular noise from the crystal structure reacting to the beam. But they found a workaround.
By averaging it out.
Yes. By aggressively averaging that highly localized, really noisy data, they effectively filter out the granular anomalies.
So the average microscopic FIB-DIC data perfectly matches the macroscopic recoil they got from the ESPI lasers.
Exactly. They basically use the laser data to keep the ion beam data honest.
That is so clever, but that only maps the surface, right?
Right, just the surface compression.
Yeah.
To measure the dangerous internal tension, the bulk material pulling apart, they have to use the cross-section warp method.
Meaning they physically slice it open.
Yes, they take a wire electrical discharge machine and just slice the titanium straight through the dimpled zone.
Here's where it gets really interesting, because as soon as they make that cut, they've completely severed the equilibrium.
The trap tension is completely released.
And the paper notes they use optical sensors to measure deplanation, which is basically just the newly cut face bulging and warping as those deep stresses finally let go.
You nailed it.
But wait, slicing the sample destroys it? I mean, why ruin a perfectly good titanium plate just to see it warp?
Because that physical deformation is the absolute key to unlocking predictive modeling. They take the exact 3D topology of that warped surface and use it to validate a finite element model.
Like a digital twin.
Exactly. They're building a highly precise mathematical digital twin of the titanium's internal forces.
So if the computer simulation warps exactly the same way the physical metal did when it was cut, they know their math is dead on.
Right. It completely eliminates the need for endless physical trial and error.
So what does this all mean for you listening to this? Well, it translates directly to safer travel.
Absolutely, because they don't have to guess anymore.
Right. With a validated 3D computer model, engineers can run thousands of simulations. They can tweak the exact diameter of the dimpling sphere or the precise kilonewtons of force applied, all mathematically.
Maximizing that crack-stopping surface armor while minimizing the dangerous internal tension.
Exactly. Keeping the aerospace components you rely on entirely intact.
And, this raises an important question. If we can now build perfect digital twins to predict the invisible trapped forces inside a solid block of titanium,
Yeah.
what other unseen stresses in our built environment, from suspension bridges to submersibles, could we map and neutralize before a failure ever has a chance to occur?